the other thing I wanted to show you with the spherical harmonics. Let me change this back to smooth POV. So all the lighting in the world, if I make like a sphere. How do we already have a sphere? So there's like, multiple things that kind of contribute to the lighting of the sphere. There's the actual lights in the scene, but there's also like, ambient lighting. There's also ambient lighting that's, computed typically from the skybox. And I know like you don't, in normal builds, you can't control that, but there's actually a new component. This is not really polished yet, so this might actually look different. But I can like, give you a little bit of peek. If I go into rendering, there's where is it? Ambient light SH2, and this actually uses second order spherical harmonics, to determine ambient lighting. And if I, plug red here, for example, now there's like a red ambient light everywhere, and you see it immediately, affects the scene, and everything's red.
Red.
Is all red. So like the first band, is literally just like ambient, it's like covers everything. But if I do the second band, this is gonna be like one side. So now it's also red, but is red, only from top. You see, and the bottom is like dark, and same like with everything, the red is from the top. Could also change it, to be like I'm gonna do blue. Blue, now it's blue from the top. And if I actually reverse it, if I like, plug -1, if I go minus, now it's blue from the bottom. If I plug it, if I plug it here, this is gonna be from one axis. So now, it's blue from this one. So it's almost like, there's like blue light kind of coming from here. And you can kind of see it on everything, over there. And then if I go into even higher ones, you're actually gonna see this kind of creates this kind of like band effect. See, and like, let me actually use the different axis one so it's a little bit clearer. I'm gonna use this one. Here we go. This should be, there's a band here and there's a band here. So this is the way that the like, the lighting is like the ambient lighting is kind of encoded, and I can actually just plug a bunch of random stuff here. So I've kind of created like this kind of funky ambient lighting, and I can actually control it. And usually, like, it's made so it actually kind of matches the environment. I'm just kind of plugging random colors in here, but actually looks kind of neat with this world. It's kind of neat looking. But essentially, it is using, the spherical harmonics to control how the ambient lighting works. So it's one of the things that's probably going to be exposed. And we'll probably add like tools so you can kind of compute it, from a texture. And then you can also blend it. So like, like if you like, move around the environment, you could like, what is that?
That is not me. That is something in the world.
That's so weird. Anyways, we want to make it like, so it's so you can like kind of blend it. So like, for example, if you move around the world, the ambient lighting will also change. So it's kind of expose like, some new options. But the basic building block that is used for that, is the spherical harmonics, which originally, I didn't because of the Gaussian splits, because they used them to encode color, but it's also useful, for this other thing. It kind of gives you like more control over stuff. I'll actually keep this on because I kind of like how it looks. I can also show you, if I create another empty object, I've added, I'm gonna, no, this works. I'm gonna add a procedural asset, procedural meshes, there's icosphere meshes, SH2. So what this does, this is like the icosphere procedural mesh, except the both colors, like vertex colors, and the radius, you can modulate them using spherical harmonics. So if I set up a render, it's actually using the ambient lighting as well of the world, so it's gonna. I'm not gonna show the colors because we can kind of see that with that, but it's kind of funky if you play with the radius, because right now it's only using the first band, which is like it's the same everywhere. I will switch it to a different material so we can kind of see positive and negative better. So go vertex color, metallic. There we go. Don't want this one. Plug in the vertex color, metallic. There we go. So I think it's like inverted by default. No, it's dark by default. Never mind. So if I actually remove this one and I only give it like the positive band, you see like it kind of creates this kind of shape. And I'm actually going to increase the number of subdivisions so it's kind of smoother. There we go. And what you're seeing is like, it's still, the base is the sphere, but what is happening, the function, the radius, is being modulated based on the direction. And this band, it goes like vertical like this, which means over here the radius is 0. As I keep increasing, it actually goes negative here. That's why this part is actually no, this is positive because the colors are inverted. It goes like it goes positive here and negative here, and it's visualized by the color. And if I change this one to be on this one, you see it kind of like rotates it too. I'm gonna plug 0 here. It's essentially the same thing, except it's on this axis. And the way you can think about spherical harmonics, I'm actually gonna grab my brush here. Brush, give me brush. I'm not used to these controllers. There we go. The way you can think about spherical harmonics, it's like having like a standing wave, except it's on a sphere. So over here, imagine we have like like you have like start and end, and you have like a wave here. You have like a wave that goes positive and it goes negative. It's just like sine wave. It's essentially this, except it's wrapped around a sphere. So on one side it goes positive, and on the other side it goes negative. And this one, it just kind of like it flips it. So like it kind of, when it goes negative, it still like flips it, so it goes like this. But essentially it's like it's this, except following a sphere, if it kind of makes sense. And this is this is the first order. That's why it's just like one like this. If I go, and it's and you have like one band like in each kind of direction. If I go here, like it also does it like in this direction. But then when I go into the higher order bands, so let's do this one, 2, you see now it does this kind of shape. And the reason for this is because for the second order, the sine wave, it goes like this, 1, 2. And as how it wraps around this, it's like you literally have it like, is literally this peak, matches this peak. Or maybe like in its reverse, but doesn't matter. This peak, is gonna match this one. This one is gonna match this one. This one's gonna match this one. So it's kind of, it's almost like it took the sine wave and like you kind of wrapped it around. And it's also like in 3 dimensions, makes things a little bit more complicated, but essentially it's this kind of principle. And what this does, it's a way of like sort of encoding information where, it can be sampled directionally. Because you can kind of combine these different bands, to create all kinds of different, functions on the surface of the sphere. So I can like, plug one here, or maybe put a negative one here, do like this thing, and do a thing here. I'm gonna do a thing here. You don't want it to be that big. You can create like, you know, all kinds of like weird shapes. And like you don't need, you know, that many parameters for this. Like the SH2, which is like, you know, second order, which has 9 coefficients, is enough, you know, to encode like the ambient ambient lighting information like this in the world, and it doesn't need much data to do it. These Gaussian splits, they use third order, which has 16 channels, and that can encode even more information. So it's essentially like a mechanism, you know, to like encode information. Because if you think about a sphere, each point of the sphere, it's a direction from the center of the sphere, you know, to that point. So if you want to like, you know, sample point on the sphere, you're essentially, you know, taking something that's inside, like this goes from the center, and you have a directional vector. And if the sphere is like unit sphere, this is, you know, just unit direction. You sample the spherical harmonic, and it gives you color, or it gives you, you know, radius, or it gives you, you know, audio amplitude for the ambisonics. So like if you have like, you know, an audio source here, the spherical harmonics, it encodes the audio channels. The audio channels are the individual coefficients, and then you sample it based on where the listener is relative to the audio source. And this is kind of cool way, like, you know, to kind of be able to visualize it. There's actually one thing I also wanted to bring in. Let me. We're also not getting any more questions. Like, if you got any more questions, make sure, like, you know, to post them before the stream ends. I'll try to get them before, like, in this ends. But if there's no more questions, we'll probably end up like rambling about things for a bit. I did want to showcase. So there's like this kind of diagram that you can kind of see a lot, like in different disciplines, because like the spherical harmonics, they're one of the like building blocks, you know, like vectors and other stuff that kind of comes up with a lot of other stuff. If you look at this diagram, this should be very familiar. But this is literally like, you know, what I've showed you with this, because I've always been like, what does this mean? Like, you know, what is this visualizing? And this is literally just the value where the spherical harmonics modulates the radius. So if I change it, you know, back, go say 0. If it's just the first band, you know, then it's literally just a sphere, you know, as the first one. If we go for the second band, the first order, you see it makes that kind of shape. That's exactly that shape. There's like, you know, 3 of them. Then the second order, you know, there's a bunch. So like if we have 1, 2, 3, 4, so this one makes this shape, you know, and this matches our shape here. And then we also, if we plug this one to this band, you know, this makes shape on a different axis. And if we plug this one here, this makes this kind of shape. Does it look familiar? Is that shape? And then this one, this is gonna, now they're kind of getting combined. And this makes this shape. So like, it's literally these shapes. And all this indicates is the radius modulated by the, you know, value of the spherical harmonics function, you know, at each point of the sphere. With like the colors indicating like where it goes positive and where it goes negative. Because, you know, if you got a sine wave, it goes, you know, it goes positive and it goes negative, positive, negative. Same here, you know, it goes positive, negative, positive, negative. And if you add like more bands, you know, this one, you can see like now it goes like, you know, 3 times. So the third order is, you know, positive, negative, positive, negative, positive, negative. Like, you know, it goes through three waves essentially. And the more orders you add, like, the more complex the shape gets, the more complex the information you can encode is.
I guess like
So
you you can almost think about it like the different frequencies that like make up a sound wave, for example, because the data that they represent is constructed out of their interference with each other.
it kind of, I mean, this kind of waves in general is like these are sort of like the basis ones, and then like you combine them to like create whatever function you want. Usually, like this is like an extreme variation, so like this is gonna be
Mm.
like this kind of like kind of showcase. But you can use these kind of to constructively and destructively like create like some kind of like smooth function. It's actually the same kind of, it's similar approach that's like used for encoding images with like JPEG, because
Oh yeah,
with JPEG what you do, you essentially vary like kind of frequency information in a block of 8 by 8 pixels. I forgot my brush. There we go. So like in JPEG you're essentially overlying, like a bunch of things, and you can have like very high frequency detail, that goes with like low frequency detail, and like it ends up like making, like if you want like very big detail, you can have a function that's that's gonna be bright here and low here, and what this is, this is gonna be like this, and then you're gonna have like information that varies a lot more, so it's gonna create like kind of bands. And if you have enough of these, you can actually construct pretty much any you can construct any image you want. What it is, you're essentially using the Fourier transform, where you translate the the information from spatial domain into frequency domain.
yeah,
You can compose any wave out of like any frequencies, as long as you have like any of them. And it's kind of the similar thing. If you had enough of these, you could, have arbitrarily precise information on the surface of a sphere. And the spherical harmonics is what makes the encoding kind of like, efficient. Especially like if you don't have too many bands, it makes it very efficient to encode low frequency detail. So like you cannot like, have like something that's like, a color that would be like in a very small area, very different. The information is very low frequency, which means it kind of varies more slowly. But for stuff like ambient lighting, that's perfect because that doesn't have very high frequency details.
yeah. We did get a couple more questions
Yeah,
actually.
there's more questions. Um, So Lucas is also asking, so far these examples use secondary SH, will there be higher order ones? So Gaussian split actually has third order ones. So like if I switch to this, you see for the Gaussian split, it goes all the way to SH15. There's also data structure for SH4. So if I switch to this, and I'll create just an empty object. And I just go data. I'm just gonna make value field. Oh, just another cool thing about these. Like I've implemented these very generically, so I can be literally spherical harmonics. And then I'm just gonna use float. Oh, actually, I forgot to add the order. So right now the hard-coded ones are all the way up to fourth order. So I can add, fourth order spherical harmonics, and these have like 25 coefficients. There's nothing that like uses these right now. I do want to add like so it actually generates the icosphere for all of these all the way up to L4. If there's interest, I can implement like arbitrary level of support, but that's gonna make it a little more complicated for the data model. And I don't think like you see like higher order ones like super often anyways, so I'll probably leave that one for later. But right now they go all the way to L4 within the data model. This is another question, how much can you change with SH with ProtoFlux? Can you drive it, for example? Yes. It's literally like, it's not that different, from other data types like matrices, or vectors. So if I grab this, let me actually I'm gonna show it with this one because it's gonna look funky. So if we go back, to this kind of thing, this is just a value, like any other. So I can drive it, and there's a new set of nodes. There's only a few basic ones. Probably gonna need some more in the future. Wait, what is happening?
Sorry, I was selecting something.
Oh, so if I go math, the spherical harmonics, you can pack them, and there's also like evaluation. So you can you can plug any spherical harmonic and evaluate value at like vector you want. This one is second order, so I'm gonna pick this one. And I pick the type float. So I can, essentially just pack it. And I go like one, go like zip. I'm gonna move this a little bit closer and say like I just wanna, animate it, like do funky stuff with it, just kind of for visualization purposes. I'll go grab time, first time, and then I'll do like simplex noise, I think. Yeah, it works. Simplex noise. It actually works because it goes electron negative too. We could also just use simplex noise. There we go. Plug this in. Go on. There we go. Plug this in. I just plug this into this, and now I have this blobby thing, whatever this is.
You should
It
try
actually looks kind of neat. That
doing
is.
lighting with it.
Yeah, hold on. Let me change the color so it's also like. Oh, that's not what I want. No, that's too much. Eh. There we go. Ooh. But I can mess with it and do like whatever stuff you want. I'm gonna do some more. I'm just gonna multiply. Where's multiply my dummy? It's in operators. There we go. I'm just gonna plug this in so I can just vary it a little bit so they're not like all the same. So I'm gonna do like, I don't know, like 3 point something, just random value. And let's do simplex too. And just go here. Oh, that's too much actually. That's too fast. There we go. I've got like this funky shape. So like you can drive them. You can like mess around with them. You can sample them. I've kind of hinted at this like a little bit earlier. So if I go math, spherical harmonics, there's the evaluate. And there's some kind of helpers because like you need to specify the spherical harmonic you want. So I want spherical harmonics L2 of type float. And the type is float. Take it out of it. Float. Did I do it wrong? I did something wrong. Spherical harmonics. What did I do wrong? This is spherical harmonics L2 float. Oh, it misspelled spherical, dummy. There we go. So I got the evaluate node. So I can actually be like, I want to know what value is at the dispersion vector, and right now there's not one, so I'm gonna do it here. Oh, it's not updated. Oh, I need to mark it as continuous up. No, that's weird. Why is it not updating by default? Something's clogged. What? What is wrong with this? Did I bork something? Might still have bugs. Yeah, it's kind of like work in progress and stuff. So like I think there's very odd. Why is this not evaluating? Yeah, normally I should be able to evaluate them, but there's something wrong right now.
Oy, oy.
Yeah, work in progress built.
Whoa, whoa.
Oh, do you?
Whoa.
Oh, there we go. You're animating. There we go. You're
Yeah,
animating the ambience.
hooked them up to ColorX Hue with this like offset for a couple of them.
Yes, there we go. That's really neat. So you can create like all kinds of like effects with that.
Whoa. It's kind of like almost like rotating. That's crazy.
It pretty much is, I think. Like they're like offset, like it's like when you combine them, like it essentially creates this kind of like rotating effect. You might have like seen it like earlier too. Is like when I was combining some of
Oh.
them, it's kind of funky. Like when you look at this too, so it's just going.
Oh wow. It's
One,
like it just like creates like a hole in the middle sometimes.
yeah.
Whoa.
One thing I'm like just hoping somebody will make with this is like a audio visualizer.
Yes.
But yeah, hopefully that also answers those extra questions. Is like you can work with them in with ProtoFlux. My goal was to essentially add a new data primitive. The way vectors are, the way matrices are. This is just another one because it's useful for so many things. So the Gaussian splits, they were sort of like the initial impulse to do it, but then I was like, oh wait, these are useful for this, and they're useful for that, and for this other thing. And I made sure the implementation is very generic. So like with any data type that does support that supports multiplication or specifically scaling, you can use it with spherical harmonics. Like you could make spherical harmonics that like has matrices on each point, which like I don't know if there's like any practical use for it, but somebody will make something crazy with it.